Sometimes air pollution is obvious, like wildfire smoke, or thick smoke belching from factories. In cases like these, it's pretty easy to imagine that breathing that air is not healthy. In contrast, sometimes there'll be an air quality alert. But when you go outside, the air doesn't seem especially bad, maybe just a bit hazy. For example, here's Connecticut on an air quality alert day. And here's Connecticut on a normal day with no air quality alert. They both look pretty similar, so what gives? Well, if we take a closer look at the air quality alert for this area of Connecticut, we can see that it's alerting us of ground level ozone. So breathing ozone must be bad for you. But if we're not seeing anything like this, how bad can it be? Well, in this video, we're going to generate some ozone and show you how bad it can be. How are we going to generate ozone, you might ask? Well, with lightning. Because, as you may or may not know, lightning generates ozone. Lightning from your typical thunderstorm actually makes a non-trivial contribution to ground level ozone. More on that later. Instead of trying to harness a lightning bolt, we built a machine that makes one. Well, obviously not a full-sized one. Our machine only produces a spark about 1 centimeter long, but it still generates enough ozone to demonstrate its caustic effects. Here is our spark-making machine. When you flip this switch, just like the name suggests, it makes a spark in this bottle. This is what it looks like. Here's a close-up. Pretty cool, right? We won't go into too much detail about how to build your own spark-making machine. A quick web search will turn up a lot of sources, and there are several ways you can go about it. You can also click on the link up here to watch a YouTube video that will show the strategy we used. But just so you can have a general idea of how it works, here's the circuit diagram for our spark-making machine. Notice there is a capacitor, an ignition coil, a dimmer switch, a gap for the spark, and it receives power from line voltage, which is right here. Now, if we look back at our machine, we can see all of those things just as they were shown on the circuit diagram. Here is the capacitor, the ignition coil, the dimmer switch, the gap for the spark, and the line voltage, which you can see right here where this wire will get plugged into an outlet. If you look closely, you can see that we've put a plastic bottle around the gap for the spark. This is just to help contain the ozone that the spark is going to be creating. When we run the actual experiment, you'll see that we even go so far as to tape the ends of the bottle to concentrate the ozone as much as possible around the rubber band. You should also note that the rubber band is not touching the spark or either of the electrodes, so anything that happens to it is not because it's being electrocuted or burned. So without further ado, let's see what happens. What you just saw was sped up, but in total it took about 20 minutes for the rubber band to break. Clearly, the spark is producing something that deteriorates the rubber band pretty drastically. And as you've probably figured out by now, that something is primarily ozone. It's being produced here just like it is in a thunderstorm. So how is it being produced? Well, what's happening is the lightning bolt, or spark, is producing a highly energetic environment. To give you an idea of just how energetic, in dry air, the required voltage difference to cause a spark to jump a gap is about 30,000 volts per centimeter. And since our gap is just about 1 centimeter, the discharge is right around 30,000 volts. So this highly energetic environment causes stable molecular species in the vicinity of the spark, like O2 oxygen gas molecules, to dissociate into reactive radicals, which in our case is atomic oxygen. These atomic oxygens are super unstable, so when they come into contact with leftover O2 molecules, they readily react to form O3, which is ozone. Of course, in reality, all this is happening lightning fast, and much closer to the spark. But you get the idea. Here is the representative reaction sequence, showing that when O2 combines with a spark, 2 atomic oxygen radicals are produced. And when O2 combines with one of those oxygen radicals, ozone is produced. Now, ozone is also reactive, so when it comes into contact with just about anything, it tends to react, which is exactly what happened when it came into contact with the rubber band. So what does this reaction look like? Well, the polymer chains that make up a rubber band look something like this, continuing on in either direction. And as you can see, they contain double bonds. Ozone reacts with those double bonds, which severs the polymer chain. This process is actually called ozonolysis, and it's really clear in our demo. You can see the rubber band getting weaker and weaker as ozone continues to sever those polymer chains until eventually it snaps. Your organs are constructed from polymers, biopolymers, so it's pretty easy to imagine what happens to your lung tissue when exposed to ozone. Yeah, breathing a significant amount of ozone is a remarkably bad idea. You might be wondering what that second rubber band is that you've seen in a couple of clips. We put it there to run a control experiment, where we show that the rubber band is breaking because of the ozone and not because it's being stretched out for a long time. If you've made it this far in the video, hopefully you're thoroughly convinced that ozone is very bad stuff. It corrodes polymers, and you really don't want it in your lungs. But wait. You've probably seen alarmist news stories about a hole in the ozone layer, and how the unintentional release of chlorofluorocarbons into the atmosphere is depleting it of ozone. In fact, the problem was so serious that eventually chlorofluorocarbons were phased out worldwide. So apparently not having ozone is a bad thing too. What's that about? Well, the beneficial ozone is in the stratosphere, the part of the atmosphere where passenger jets cruise. Ozone in the stratosphere absorbs ultraviolet photons coming from the sun. This protects us from damaging ultraviolet radiation that causes sunburn and skin cancer. If chlorofluorocarbons are released into the atmosphere, they drift up into the stratosphere where they deplete ozone by reacting it away into other stuff. This leaves a hole in the ozone layer through which the damaging ultraviolet photons can now penetrate. So in summary, ozone near the ground? Bad. Ozone high in the atmosphere? Good. Now, if you are planning to do this experiment by yourself, we highly advise you to first read the safety considerations in our lab write-up, which can be found in the description. Obviously, don't touch the spark or the hot electrodes, but another thing to note is to not touch the capacitor right after you've had the spark on, because it will be fully charged and give you a very big shock. To show you, we've taped a very thin piece of wire to the end of a ruler, and we're going to touch the capacitor with it right after the spark has been on. We've just turned off the spark, so the capacitor is fully charged. That's a pretty big spark, so make sure you're being careful. Thank you so much for watching, and we hope you learned something and had fun.